When we look up at the night sky, we see stars, thousands of them scattered across a seemingly endless canvas of darkness. But what most of us rarely consider is that every star we see belongs to a far larger structure, a galaxy. Our sun is not a lone wanderer, but one of hundreds of billions of stars orbiting in a vast stellar city called the Milky Way. And the Milky Way itself is just one of trillions of galaxies, each with its own sprawling collection of stars, planets, gas clouds, black holes, and mysterious dark matter. Galaxies are the true building blocks of the universe. They shape its large-scale architecture, they nurture the birth of stars, and they dictate the cosmic environment in which planets and ultimately life can exist. They are not just clusters of stars, but cosmic ecosystems, bound together by gravity and evolving over billions of years. The story of galaxies is also the story of the universe itself. From the first clumps of matter after the Big Bang to the majestic spirals we see today, galaxies reveal the long journey of cosmic evolution. They are the stage upon which the universe's grand drama has played out. The formation of elements, the ignition of stars, the collapse of black holes, and the merging of entire stellar civilizations. In this film, we will journey across 6 chapters. We will begin with the foundations of galactic formation in the early universe, explore some of the most iconic galactic structures, confront the mysteries that still baffle astronomers, and understand what role galaxies play in our own existence. Finally, we will look ahead to the distant cosmic future, when galaxies themselves will decide the fate of the universe. This is the story of galaxies, the cities of the cosmos. I think it's safe to say that galaxies are pretty cool. Like, sure, our planet Earth is nice, I guess, but compared to these sprawling collections of stars and dust, it's really just a speck. In fact, as far as we can tell, our planetary system is pretty average. So if you want to learn more about how the universe works, you got to start with galaxies. And fortunately for you, that's what this channel is all about. It's a series of 10 one-hour episodes that takes you on a journey through the evolution of galaxies, from the first small structures that formed in the early universe all the way to our Milky Way today. It's taught me so much. Like, seriously, I wish something like this existed when I was in college. But better late than never, right? So let's get started. The story of galaxies starts before there even were galaxies. To be clear, it definitely started with the Big Bang. You know that. But the details matter. When the universe was born, space was so hot and dense that atoms couldn't form. Everything was a swirling sea of subatomic particles. It was also opaque. Photons, or particles of light, couldn't pass through the haze, so light as we know it didn't exist either. But about 380,000 years after the Big Bang, the universe had expanded and cooled enough for protons and neutrons to combine and form atomic nuclei. Electrons then combined with those nuclei to form neutral atoms. And with that, the universe went from being opaque to transparent. Light could finally travel freely. Space was no longer a thick fog, and the universe entered what's called the Dark Ages. But don't get too excited. This was not a time of great enlightenment. Not only were there no stars or galaxies, there wasn't even any normal matter. The only stuff out there was a thin soup of hydrogen and helium. So it was dark because there was no light, and it was empty because there was little matter to speak of. That is, except for the tiny fluctuations in density. Some regions were ever so slightly more dense than others. We're talking 1 part in 100,000. But those differences mattered. Those variations would become the seeds of the universe's large-scale structure. You see, those variations were imprinted on the universe in the first trillionth of a second after the Big Bang. During a period known as inflation, the universe expanded exponentially, faster than the speed of light. Different parts of the universe grew at slightly different rates, creating tiny variations in space. Then, as the universe continued to expand over the next few 100 million years, gravity pulled matter together in the denser regions, gradually increasing the size of those regions and the variations. But there was a problem. Matter was barely interacting with itself. Normal matter, that is. We know that because the universe was filled with a sea of radiation. Photons bounced off free electrons and prevented atoms from forming. But there was also a mysterious substance called dark matter. Dark matter is invisible because it doesn't interact with light or other forms of electromagnetic radiation. but it does feel the pull of gravity. So while regular matter was locked up in the plasma, dark matter was able to clump together in the regions where gravity was slightly stronger. Over tens of millions of years, these dark matter halos grew into vast, invisible structures that acted as scaffolding for galaxies. Regular matter eventually did the same thing. Stars formed within the denser regions, and with that, the universe went from dark to light. Now, I should note that most of the mass in galaxies is dark matter, but it turns out that most of the action happens in the regular matter, which includes everything that we as humans are made of. The first stars to form in this era were massive and extremely hot. They burned through their fuel so quickly that they lived fast and died young. We call these stars population 3. Their intense ultraviolet radiation blasted away the surrounding hydrogen, making the universe transparent in a deeper sense. Again, it was no longer just a physical transparency. Now it was full of light, or at least ionized gas, which could reflect and refract light. This era is called reionization. We know relatively little about it because it happened so long ago and left behind almost no evidence. The light from the first stars was so energetic that it completely stripped hydrogen atoms of their electrons. But as the universe expanded, those electrons eventually recombined with protons to form neutral hydrogen. This is why most of the universe today is still mostly neutral hydrogen, which doesn't interact with visible light. So the first stars and galaxies were both born and hidden from view. It's kind of like if your great-great-grandparents had been incredibly bright but short-lived, like a shooting star. You wouldn't know about them unless you were specifically looking for the faint echoes of their light. Eventually, though, regular matter became abundant, enough to block the harsh radiation of those early stars and allow more typical stars and planets to form. These are the stars and galaxies we see around us today. And here's a fun fact. Most galaxies have 2 of them. Astronomers aren't exactly sure why this is the case, but it might have to do with the dark matter halos that surround galaxies. Dark matter seems to have a natural tendency to spin, and if that's the case, it's possible that this spin affects the distribution of regular matter. These smaller galaxies then acted as building blocks for larger structures. Over billions of years, they came together in a never-ending cycle of collisions and mergers. Eventually, these processes led to the large galaxies we see today. This is what's called hierarchical formation. And it's thought to explain why most galaxies today are spirals or ellipticals. Spirals, like our Milky Way, tend to have lots of gas and dust and lots of young stars. Ellipticals tend to have less gas and dust and older stars. It's not 100% clear why this happened, but many astronomers believe that it has to do with the kinds of galaxies that merge. Spirals tend to merge with other spirals, while ellipticals often merge with other ellipticals, but they can also merge with spirals and become even more elliptical. Our own Milky Way is a spiral galaxy that formed through the gradual merging of smaller galaxies. Its stellar halo is filled with remnants of those long-digested dwarf galaxies. It's hard to study these remnants because they're so faint, but they provide a tangible connection to the universe's past. They're real-life fossils. It's only in the last few billion years that galaxies have begun to settle down. Large galaxies like the Milky Way have mostly stopped forming new stars, though that doesn't mean they're boring. Galaxies can still undergo major mergers and interact gravitationally with each other. Even if they don't actually collide, the mutual gravitational tugging can trigger bouts of star formation. And who knows, maybe even kick off the formation of new galaxies. In the end, we've come full circle. Our modern universe looks so much like it did in those early stages, not because the old stuff is still around, but because new stuff is constantly being made. Stuff we see today isn't like the stuff that existed back then. It's recycled. All the carbon in our bodies, the oxygen we breathe, even the iron in our blood, it all began as a cloud of hydrogen and helium. Galaxies are recycling that material continuously. Every time a star explodes, it throws its guts out into intergalactic space. This creates new pockets of dense gas and dust that will one day collapse into new stars and planets. In a few billion years, the stuff that makes us will be part of some alien creature living on some alien world. And in a few billion more, that stuff will be part of yet another generation of stars. In short, the stuff that makes galaxies keeps on recycling itself over and over again. What if I told you that our entire universe could be explained by 4 simple pictures? We've been taught that the fundamental forces of nature can be summarized in just 4 equations. But did you know that all the variety of galaxies out there can be categorized into 4 main shapes? Well, in this video, we're going to explain what these 4 galactic forms are, how they came to be, and why they are so incredibly diverse. So sit tight, because we're about to go on a journey through the grand tapestry of the cosmos, exploring the inspiring array of galactic forms. But before we delve into the intricacies of these celestial wonders, we urge you to support our work with a thumbs up. Your support means everything to us and keeps us motivated to bring you the best content possible. Now, let's embark on this cosmic adventure. Step into a realm where the birth of galaxies unfolds and witness the mesmerizing dance of matter and energy that gives rise to these majestic cosmic structures. We begin our journey with a mind-boggling fact. All galaxies, regardless of their size or shape, emerge from tiny, almost imperceptible ripples in the fabric of space-time. These ripples, known as quantum fluctuations, provide the initial seeds for galaxy formation. As the universe expands, these seeds act as gravitational wells, drawing in surrounding matter. Over billions of years, this process gradually evolves into the majestic galaxies we observe today. But the story doesn't end there. The life cycle of a galaxy is a tale of continuous evolution. Mergers and collisions with other galaxies are not rare occurrences. They're fundamental events that leave an indelible mark on the structure and evolution of galaxies. When galaxies collide, their stars, gas, and dust are violently disrupted. The aftermath of these cosmic clashes can give rise to a dazzling array of shapes. Some galaxies emerge as graceful spirals, while others take on the form of irregulars. Each collision brings with it a unique set of circumstances, resulting in a kaleidoscope of possibilities. But the influence of these interactions extends far beyond mere changes in shape. Collisions can trigger intense periods of star formation, giving rise to brilliant stellar nurseries. On the other hand, they can also lead to the expulsion of gas and dust, quenching star formation and leaving galaxies in a state of decline. And what of those enigmatic black holes residing at the hearts of many galaxies? Their role in shaping galaxies is nothing short of profound. These invisible cosmic titans exert a gravitational influence that can extend hundreds of thousands of light years into the surrounding space. As galaxies evolve, their black holes grow, consuming matter and increasing their mass. The energy released by this consumption can drive powerful outflows, profoundly affecting the distribution of gas and the rate of star formation. The interplay between galaxies and their central black holes is a cosmic dance of both creation and destruction, constantly reshaping these majestic structures. As we continue our exploration, keep in mind that the story of galaxy formation is not merely a tale of the past. It is a story that continues to unfold in the present. Every star that shines, every cloud of gas and dust that coalesces, every collision that occurs adds a new chapter to the ever-evolving saga of galaxies. Understanding how galaxies form is not just about unraveling the secrets of the past. It is about comprehending the very essence of the universe we inhabit, now that we understand how galaxies first emerged. The next question becomes, what shapes do these vast cosmic cities take, and what makes them so distinct? Galaxies are not uniform. Instead, they display a remarkable diversity of sizes, structures, and histories. Some are graceful spirals, others are featureless giants. And still others are chaotic dwarfs scattered across the universe like small villages on the outskirts of a great empire. To appreciate their complexity, we'll explore the most iconic galactic forms, beginning with our own home, the Milky Way. The Milky Way is a barred spiral galaxy, a sprawling disk of stars, dust, and gas that measures about 100,000 light-years across. At its heart lies a central bar-shaped concentration of stars, from which spiral arms unfurl like luminous rivers. These spiral arms are not fixed structures but dynamic density waves, regions where gas is compressed, triggering bursts of star formation. Within them, stars like our Sun are born, live their lives, and eventually die. Orbiting the galactic center at 220 kilometers per second, our Sun takes about 230 million years to complete one lap, a galactic year. Its motion places us within a vibrant neighborhood. The Orion Arm, a minor spiral branch filled with clusters of young stars and nebulae. At the very center of the Milky Way lurks a supermassive black hole, Sagittarius A*, with a mass of over 4 million suns, though invisible directly. Its presence is revealed through the rapid orbits of nearby stars, some whipping around it in just a few years. This black hole is not unique to the Milky Way. Nearly every large galaxy harbors such a monster in its core. These central black holes are thought to play an essential role in regulating the growth of galaxies, shaping their star formation histories. Andromeda. Our sister galaxy just beyond the Milky Way lies Andromeda, our nearest large galactic neighbor, slightly larger than the Milky Way. Andromeda is also a spiral galaxy, stretching some 220,000 light-years across. What makes Andromeda especially significant is its future. In about 4 billion years, it will collide with the Milky Way. This titanic merger will not be a destructive explosion, but a slow, graceful dance of gravity. Stars will be flung into new orbits, tidal tails of gas will stream outward, and eventually the two galaxies will merge into a single giant elliptical. Andromeda's sheer size and proximity have made it a cornerstone in our understanding of galaxies. In the 1920s, Edwin Hubble's observations of variable stars in Andromeda proved that it was not a nearby nebula, as once thought, but a separate galaxy, a revelation that transformed our view of the universe. Elliptical giants, the behemoths of the universe beyond spirals, another major galactic form dominates. Elliptical galaxies. Unlike spirals, these galaxies lack arms or disks. They are rounded, smooth, and often enormous, containing trillions of stars. The largest of all, called giant ellipticals, can stretch over 1 million light-years across. These giants typically form from the mergers of smaller galaxies. When spirals collide, their ordered disks are disrupted, and their stars are redistributed into more random orbits, creating the smooth, featureless appearance of an elliptical. Because gas is often consumed or expelled during these violent encounters, elliptical galaxies tend to be red and dead, populated mostly by old reddish stars, with little new star formation. One famous example is M87, the central galaxy of the Virgo cluster. It houses a supermassive black hole, 6.5 billion times the mass of the Sun. The very black hole, imaged for the first time in 2019 by the Event Horizon Telescope. M87 is a prime example of how galactic scale and central black holes intertwine, creating systems of extraordinary power. Irregular dwarfs. The cosmic outliers. Not all galaxies fit neatly into spirals or ellipticals. Many are small, irregularly shaped dwarfs. These galaxies, often containing only a few billion stars or less, are scattered throughout the universe and often serve as building blocks for larger galaxies. The large and small Magellanic Clouds, visible in the southern hemisphere, are prime examples. They orbit the Milky Way as satellite galaxies, their shapes distorted by our galaxy's gravity. Within them, star formation is still ongoing, offering a glimpse of conditions similar to the early universe. Despite their modest size, dwarf galaxies are scientifically crucial. They help astronomers test theories of dark matter and galaxy formation, and they act as living fossils, relics of the processes that built up today's giant galaxies. Galactic classification, the Hubble sequence, to make sense of these diverse forms. Astronomers use the Hubble sequence, a diagram proposed by Edwin Hubble in 1926. It classifies galaxies into ellipticals, spirals, barred spirals, and irregulars. A system often nicknamed the Hubble tuning fork. Though once thought to represent an evolutionary sequence, we now know it is more of a classification tool, with galaxies able to change types through mergers and interactions. Taken together, these iconic galactic forms show us that galaxies are not static objects, but evolving systems. Spirals can merge into ellipticals, dwarfs can be torn apart and absorbed, and massive black holes can shape entire star systems from their centers. Galaxies are not just islands of stars, but dynamic, living structures, each with its own history, environment, and fate. Throughout this journey, we've witnessed the astonishing diversity of galaxies, havens of stars and cosmic cradles of life, each with its unique story to tell. Now we invite you to become part of that narrative. Share your thoughts, insights, and questions in the comments below. Together, let's continue the conversation and deepen our understanding of the cosmos. As we look up at the night sky, May we forever be filled with awe and wonder at the beauty and complexity of the universe we call home. Our quest to understand the birth, life, and death of galaxies is an epic journey into the grand theater of the cosmos. Like a director weaving an intricate narrative, gravity orchestrates the movements of celestial bodies, shaping not just their destinies, but the very essence of the universe. Welcome to Cosmos in a Minute, where we bring you the latest news from the world of space exploration and research. Today, let's embark on a thrilling exploration of the unseen forces that bind galaxies together, uncover the secrets of dark matter, and shed light on the profound mysteries that lie at the heart of these majestic cosmic structures. For all that we know about galaxies, their shapes, their stars, their growth over billions of years, a deeper truth remains. The visible matter, the stars and gas that shine across the night sky, is only a small fraction of what galaxies really are. Most of their substance is hidden, invisible to telescopes, and detectable only through its gravitational pull. The study of galaxies, therefore, is also the study of mysteries, of dark matter, clustering, and missing pieces of the cosmic puzzle. The invisible halo. Dark matter's grip. When astronomers in the 20th century measured the speeds of stars orbiting in galaxies, they found something baffling. The stars far from the galactic center were moving far too quickly to be held by the gravity of visible matter alone. By Newton's laws, the outer stars should have flown away into intergalactic space. Yet they didn't. They remained bound to the galaxy. The only explanation was that galaxies contain far more mass than we can see. This unseen mass became known as dark matter. Observations suggest that dark matter makes up about 85% of a galaxy's total mass, enveloping it in a vast, spherical halo. Though invisible, these halos provide the gravitational glue that holds galaxies together, and even the cosmic web itself. But what exactly is dark matter? No one knows. It does not emit, absorb, or reflect light. It does not interact with ordinary matter, except through gravity. Some theories suggest it could be made of exotic particles beyond the standard model of physics. Candidates like WIMPs, weakly interacting massive particles, or ixions. Others propose more radical ideas, such as modifications to the laws of gravity themselves. Despite decades of searches, dark matter remains elusive, one of the great unsolved mysteries of modern science. Why galaxies, cluster galaxies, are not evenly spread across the universe? Instead, they gather into groups, clusters, and superclusters, linked together by cosmic filaments. But why do galaxies prefer to cluster? The answer lies again in gravity, amplified by dark matter. Over billions of years, the small density fluctuations left over from the Big Bang grew under gravity's pull, creating the cosmic web. Galaxies fell into these structures, forming clusters where filaments intersected. One famous example is the Coma cluster, containing thousands of galaxies bound together in a gravitational ballet. In such environments, galaxies interact, collide, and merge more frequently, shaping their evolution. Yet the details remain puzzling. Why do some clusters contain giant ellipticals, while others preserve more spirals? Why do some galaxies and clusters shut down star formation, while isolated galaxies continue to thrive? These questions connect the fate of galaxies not just to their own properties, but to their cosmic environment.
Wow.
The missing satellite problem. When cosmologists simulate the growth of galaxies using dark matter models, they predict that large galaxies like the Milky Way should be surrounded by hundreds, even thousands, of small dwarf galaxies. Yet in reality, we see only a few dozen. This discrepancy is known as the missing satellite problem. Where are the missing dwarfs? Some may be so faint and diffuse that we simply haven't detected them yet. Modern surveys have begun uncovering ultra-faint dwarfs, ghostly galaxies with only a few thousand stars. Others may have formed without enough gas to make stars, remaining dark matter clumps invisible to us. Another possibility is that stellar feedback, the energy from supernova and young stars, blew gas out of many small galaxies before they could form stars, leaving them barren. This mystery has profound implications. If dark matter is truly the scaffolding of galaxies, then understanding its smallest structures could reveal the very nature of the unseen universe. Galactic cannibalism and stellar streams, another mystery of galactic evolution, is the evidence of constant cannibalism. Our Milky Way is devouring smaller galaxies even now.
Oh,
The Sagittarius dwarf galaxy is being torn apart, leaving behind a trail of stars, a stellar stream wrapping around our galaxy. These stellar streams are like archaeological layers, revealing the Milky Way's violent history of growth through mergers. By mapping them, astronomers can reconstruct the dark matter halo's shape and distribution. Yet many streams show anomalies, as if disturbed by unseen substructures, perhaps clumps of dark matter that never formed stars. If confirmed, these disturbances would be direct evidence of the invisible. The role of supermassive black holes. Finally, at the cores of galaxies, supermassive black holes raise another frontier of mystery. How did they grow so large, so fast, in the early universe? Observations from the James Webb Space Telescope have revealed quasars, galaxies, powered by actively feeding black holes, existing less than 1 billion years after the Big Bang. Their sheer size defies our current models of black hole growth. Did they form directly from collapsing gas clouds, skipping the smaller stellar stage? Or did conditions in the early universe allow matter to accrete at extraordinary rates? These questions cut to the heart of galaxy formation. Because black holes and galaxies seem to co-evolve, solving one puzzle may unravel the other. In the grand tapestry of the cosmos, galaxies stand as both the grandest and most intimate of structures. Grand because they span unimaginable distances, each a city of stars. Intimate because their birth, life, and death play out in a story as old as time itself. We have come a long way in deciphering this story, yet we find ourselves at a pivotal moment. The mysteries at the heart of galaxies demand a new era of exploration, one that pushes the boundaries of our understanding and challenges the very foundations of our knowledge. Just as the ancient astronomers traced the paths of the stars to understand the rhythms of the seasons, so too must we peer into the abyss of the unknown to unlock the secrets of the cosmos. The dawn of this new era is marked by unprecedented collaborations between scientists and engineers, uniting minds from across the globe. Together, they are crafting instruments of unparalleled precision and power, venturing into realms of the cosmos previously untouched by human endeavor. At the forefront of this revolution stands the James Webb Space Telescope, a marvel of engineering and scientific brilliance. With its advanced detectors and infrared capabilities, it peers deep into the universe, unveiling the birth cries of the first galaxies and the whispers of ancient starlight. Other observatories join this cosmic chorus, each contributing a unique perspective to the grand symphony of discovery. The Hubble Space Telescope continues its legacy of groundbreaking observations, while next-generation ground-based telescopes push the limits of what is possible here on Earth. Yet, the most profound mysteries often lie hidden in plain sight. Take, for instance, the enigmatic Fast Radio Telescope, a persistent signal from distant galaxies that has baffled astronomers. Could it be a harbinger of an advanced alien civilization? Or does it hold clues to the nature of dark matter or other hidden dimensions? As we delve deeper into these cosmic enigmas, we find ourselves on the brink of paradigm shifts that could redefine our place in the universe. For what if we discover that the very fabric of space-time is woven with threads of quantum foam, or that the elusive dark sector of the universe is not a realm apart, but an integral part of our own? Such revelations would not just expand our knowledge, but transform our understanding of the cosmos and our place within it. But the pursuit of knowledge is not a solitary endeavor. It is a shared human adventure, a testament to our insatiable curiosity and unquenchable thirst for understanding. In the tapestry of human history, the story of our cosmic quest is deeply intertwined with the exploration of our planet. For as we gaze at the stars, we are reminded of the fragility and beauty of our home. And in that realization, we find the inspiration to protect and preserve it. The challenges we face are not merely scientific, but societal and philosophical as well. The very definition of what it means to be human is put to the test as we confront the profound implications of our discoveries. Are we alone in this vast universe? What is the nature of consciousness and the self? How did life arise, and what is its ultimate destiny? These are the profound questions that drive our exploration of the cosmos. In the tapestry of human achievement, The story of our cosmic quest is a thread that runs through the ages. From the earliest astronomers who charted the heavens to the pioneers of modern space exploration, each generation has added its own colors to this grand design. As we stand on the threshold of a new era of discovery, we carry with us the hopes and dreams of those who came before us. It is our responsibility to weave the threads of our discoveries into the fabric of human knowledge, creating a masterpiece that inspires awe and wonder in generations to come. And so we press on, driven by an insatiable curiosity and the profound belief that the universe holds answers to the deepest questions of existence. For in the grand tapestry of the cosmos, we are but a small and fragile species, yet our quest for knowledge has no bounds. The mysteries at the heart of galaxies beckon us to unravel them, and we shall heed their call. We keep finding ourselves at the center of everything. The Earth is at the center of the solar system. The Sun is at the center of the Milky Way, and yet both are whizzing around as part of something much bigger. It's easy to forget that the solar system is just one resident of the Milky Way galaxy, orbiting a galactic core along with hundreds of billions of other stars. To understand how our planetary system came to be, it helps to know where exactly in the galaxy we live. It's me, and this is minute Earth. Our solar system resides about 2/3 of the way out from the center of the Milky Way, which is pretty far from the galactic core, but not so far that we're out in the cold. If our planetary system were any farther away from the galactic center, there wouldn't be enough heavy elements around to form rocky planets like Earth, and it's those elements that make life as we know it possible. That's because the ingredients for life are not simple. Take oxygen, for example. You can't find pure oxygen in nature on Earth. That's because it's highly reactive and quickly bonds with other elements. Most of Earth's oxygen is locked up in rocks and soil, but some is also dissolved in water and floating around in the atmosphere as an essential ingredient for life. Oxygen is also incredibly abundant, making up 47% of Earth's surface by mass. That abundance is no accident. Before Earth formed, the Sun and all the planets were floating in a giant cloud of gas and dust, and that cloud was rich in oxygen, because it had been forged in the cores of long-dead stars. Those stars exploded in spectacular supernova, scattering their guts across the galaxy. And that cosmic recycling of matter is how our solar system got its start. But the recipe for life doesn't end there. Each time a star explodes, it disperses elements heavier than helium into the galaxy. This material drifts into new clouds, eventually forming new stars and planets, and continuing the cycle of stellar creation. If the ingredients for life are common, it's because stars and galaxies keep recycling these elements again and again. And our location in the galaxy is actually pretty ideal for supporting life as we know it. Within the Milky Way, there are areas with more and areas with less dense pockets of gas and dust. And our solar system lies in a relatively calm region known as the galactic habitable zone. Too close to the center of the galaxy, the dense crowds of stars would make life precarious. Not only would frequent supernova bombard Earth with dangerous radiation, but short, intense bursts of energy could actually strip away Earth's atmosphere. Too far from the center, and our solar system would be stuck in an oxygen-starved corner of the galaxy. There simply wouldn't be enough heavy elements for Earth to have formed at all. So our planetary system lies in the sweet spot, where there are enough stars to recycle the ingredients for life, without being so close that those stars rip apart our planet. To think of it another way, the Milky Way galaxy is like a big bowl of oatmeal. We are somewhere in the middle of the bowl, and the further we are from the center of the galaxy, the thinner the gruel becomes. Eventually, if we go far enough, we will find ourselves in a part of the galaxy with so few ingredients for life that things just don't happen. There are places in the galaxy where there is so much radiation that it would tear apart any planets that form there. And there are places where there is so little oxygen that any planets would be lifeless. But here in the middle, life is possible. Of course, just because life is possible doesn't mean it's easy. Our solar system still has to contend with the occasional close encounter with other stars. As we hurtle through the galaxy, sometimes we come close to other star systems. And when that happens, we might get a brief visit from a rogue asteroid or a barrage of harmful radiation. Any of these could threaten life on Earth. In fact, Some scientists speculate that Earth's atmosphere may have formed partly as a result of a near collision with a rogue planet. In the grand scheme of things, though, our galactic neighborhood is pretty peaceful. We're in the habitable zone, but we're not rubbing shoulders with too many other star systems. And that means that while we're certainly not alone in the universe, we are still pretty far away from our galactic neighbors. The solar system is not an isolated island. It's part of a galactic city, a busy hub of hundreds of billions of stars, and a home to at least one other kind of life. We tend to think of the solar system as a static place, but it's really a dynamic environment shaped by gravity. It's continually flying through space, with the sun and its planets in tow. And in a few billion years, it will experience an event so cataclysmic, it will change the face of the galaxy. But first, let's take a closer look at what's happening right now. Although the solar system has its own gravity, it's not strong enough to overcome the much stronger gravitational forces of the Milky Way. As a result, the sun and its planets are forever bound to our galaxy, making hundreds of billions of orbits around the galactic center. Each orbit takes about 230 million years. And during each trip, Earth experiences subtle variations in gravity from neighboring stars and clouds of gas and dust. These close encounters are rare because stars are so far apart. Even the closest stars are more than 4 light-years away. But because the Milky Way is a flat pancake with a central bulge, some objects will cross its path. One such visitor is the Omicron Centauri dwarf galaxy, which will pass close enough to the solar system in about 100,000 years to noticeably tug on the outermost stars, including our very own. As they move, those stars will drag along with them clouds of comets in a region called the Kuiper Belt. This could trigger a wave of comet impacts on Earth and other inner solar system planets. These near misses will leave telltale scars on the planet's surfaces. Meanwhile, the most dramatic future event for the solar system will occur in about 4 billion years, when the Milky Way collides with its nearest large neighbor, the Andromeda galaxy. By then, the two spiral galaxies will have been drawn together by their mutual gravity and will begin a slow dance of merging. Some astronomers predict that Earth won't even exist in 4 billion years, so no one will be around to witness this spectacular collision. Others argue that life will continue as usual for billions of years. Either way, the collision will be a close one. The two galaxies will pass through each other like two ships in the night, but not too closely. Stars are so far apart that collisions between individual stars will be rare. Instead, the gravitational pull of countless stars will conspire to hurl Earth and the other planets into new orbits. The night sky will be filled with a breathtaking vista of colliding galaxies. Eventually, the Milky Way and Andromeda will fuse into a single giant elliptical, sometimes nicknamed Milkomeda. It might look like a big ball of yarn, but it will be smooth and featureless compared to the intricately shaped spiral arms of its predecessors. Although the solar system will survive intact, it will be a very different place. The familiar constellations will be turned upside down, and many stars will seem brighter or dimmer. The cosmic dance will settle only when the two sets of stars have settled into a new equilibrium. All this will happen against the backdrop of the Milky Way's central black hole, Sagittarius A*. Although Earth is more than 26,000 light-years away from the galactic core, the black hole's influence stretches far out into the galaxy, affecting the dynamics of the entire Milky Way. Today, the black hole is relatively quiet, but its activity has waxed and waned over cosmic time. About 3 million years ago, it may have produced enormous jets of energy that blasted up through the galaxy, now visible as giant gamma-ray bubbles stretching above and below the galactic plane. Such outbursts, if frequent, could alter the conditions for life across large regions of the galaxy. So the black hole's behavior is part of what makes the Milky Way such a special place. It's a dynamic environment that has shaped the solar system's history and will continue to do so for billions more years. When we say Earth is part of the Milky Way, we mean more than just a postal address. The Milky Way provided the heavy elements, the stable orbital environment, and the relative calm needed for life to evolve. Every atom in our bodies came from a star that exploded in a distant part of the galaxy. The sun formed out of this recycled material, and Earth, with its oceans, continents, and atmosphere, is perfectly situated in the galaxy to be habitable. Our planet is just one of many worlds orbiting a typical star. Yet Earth is the only place we know of that can support life. And despite our tendency to think of ourselves as special, we are really just citizens of a galactic city. From outside, Earth is invisible. Even the sun is just another star among hundreds of billions. Our entire history, every civilization, every thought ever conceived is confined to a speck of dust orbiting a modest star in one corner of a spiral arm. But from within, that same perspective is transformative. To understand galaxies is to understand the larger stage upon which our story unfolds, and to realize that our world, however small, is deeply connected to the grand architecture of the universe. We are all made of star stuff. So when we look up into the night sky, we see the places that we come from. But how did we learn that? What does it mean to be from here? We know now that we live on a tiny planet orbiting an average star in an average galaxy, but our cosmic address used to be a lot less specific. For most of human history, we didn't even know that we lived in a galaxy, and it took a very long time for us to understand that the stars we see are divided into two categories, those in our galaxy and those in other galaxies. The ancient Greeks looked up and saw the stars that twinkled in the night sky. They noticed that some of them seemed to change their position slightly over time. They followed these paths and realized that the stars were moving in circles around a fixed point in the sky, the North Star. They concluded that the Earth must be at the center of the universe, with the other stars revolving around us. They also noticed that there were some parts of the sky where no stars could be seen. They called these regions black holes because they were empty, without stars. Our galaxy is bigger than any other galaxy. That's why they couldn't see past it. They thought that the stars were just dots in the sky. They didn't realize that many of them were actually whole other galaxies. In reality, the universe is made up of billions of galaxies. Each galaxy contains billions of stars. The Milky Way is just one of these galaxies. In the 17th century, Galileo Galilei pointed his telescope at the stars and realized that many of them were actually planets. This discovery supported the heliocentric model of the solar system proposed by Nicolaus Copernicus, which placed the sun rather than the Earth at the center. But Galileo couldn't see any other galaxies because the stars were so far away. They looked like a blurry mass in his telescope. He named this region the Milky Sea, or in Latin, the Via Lactea. In the 18th century, William Herschel began systematically surveying the sky in an attempt to map out all the stars. He was looking for comets, but he ended up discovering the planet Uranus. His systematic approach laid the groundwork for modern astronomy. Meanwhile, new instruments were revealing more and more about the universe. In 1845, a German astronomer named Johann Gottfried Galle mapped out a large group of stars in the constellation of Andromeda. He called this group the Andromeda Nebula because it looked like a cloud of fog. Today we know that this structure is actually a spiral galaxy similar to our own Milky Way. In the 19th century, Lord Rosse built the largest telescope in the world. With this telescope, he observed a number of nebulae and was able to measure their distances. He also made a map of the Milky Way and divided it into 60 sections. This map was the first accurate representation of our galaxy. In the early 20th century, Edwin Hubble used a 100-inch telescope at Mount Wilson Observatory in California to measure the distance to the Andromeda Galaxy. He found that it was much farther away than the other galaxies that he had studied. This led him to conclude that the Milky Way is just one galaxy among many in the universe. These discoveries have had a profound impact on our understanding of the universe. When you look up at the night sky, what do you see? To the ancient astronomers, the stars appeared sprinkled across a dark blue void. They saw themselves as the center of creation with the sun and moon revolving around them. But our view of the heavens has changed dramatically over the centuries. Today we know that the universe is neither empty nor fixed. It's filled with objects that were invisible to the unaided eye, and it's teeming with motion and change. We have gone from seeing a handful of stars to glimpsing billions of galaxies. And this journey has revealed not just the vastness of the universe, but also our place within it. In 1610, the first telescopic view of the heavens revealed the craters and mountains on the moon, the phases of Venus, and 4 satellites of Jupiter. This new way of seeing the heavens suggested that Earth was not the center of the universe as long believed, but merely one planet among many. By the mid-19th century, Astrophotography had advanced, capturing more stars and nebulae. And then in 1845, German astronomer Johann Friedrich Julius Schmidt trained a telescope on a star cluster near the North Star. He expected to find an ordinary group of stars, but instead discovered a strange, fuzzy object. At first, he thought it might be a comet, but comets have distinct shapes. This object was round like a circle. He took more pictures and watched as the object slowly changed shape. Finally, it dawned on him. This was not a comet, but a cloud of gas and dust, a nebula. He had seen a birth of a star, and the implications were staggering. Our universe, once thought immutable, was changing, evolving over time. In the 1920s, American astronomer Edwin Hubble made an even more stunning discovery. He found that the universe was expanding. As galaxies receded from Earth, they were flung away on the wings of a cosmic explosion. This view of the universe as a dynamic, ever-changing place set the stage for a revolution in our understanding of the cosmos. Then in 1995, another telescope bearing Hubble's name transformed our view again. In 1995, astronomers pointed the Hubble Space Telescope at a seemingly empty patch of sky for 10 days. The resulting image, known as the Hubble Deep Field, revealed thousands of galaxies, some so faint and distant that their light had traveled for more than 10 billion years. This image was a revelation. The universe is filled with galaxies in every direction, at every stage of evolution. What once seemed empty was, in truth, crowded with cosmic cities stretching across time and space. In the early 2000s, the Sloan Digital Sky Survey took the next step. Using a dedicated telescope in New Mexico, it systematically mapped millions of galaxies, creating three-dimensional charts of the universe. These maps revealed the large-scale structure of the cosmos: filaments, walls, and voids, the cosmic web itself. Suddenly, galaxies were not just individual objects, but parts of a vast interconnected architecture. And today, the James Webb Space Telescope is pushing the frontier further still. With its infrared vision, Webb can peer through dust clouds and detect the faint light of galaxies formed just a few hundred million years after the Big Bang. Already, Webb has revealed galaxies earlier and more massive than expected. Challenging models of how fast cosmic structures could grow, we are now witnessing the dawn of galactic history, the very first cities of the cosmos, glowing faintly in a young universe. Over the decades, our views of the universe have changed dramatically. From a sprinkling of stars on a dark background to a vast, dynamic, ever-changing cosmos filled with galaxies. Now we are entering yet another new phase. Thanks to telescopes like JWST, we are no longer just discovering galaxies. We are characterizing them, measuring their properties, and using them to understand the history of the universe. But perhaps most important, these instruments are reminding us that the universe is not something distant and dead. It's alive with activity. Stars are born and die. Galaxies collide and merge. The web of cosmic matter and energy is in a constant state of flux, a grand cosmic dance that has been playing out for billions of years, and we are fortunate enough to witness it. In a universe of trillions of galaxies, each containing trillions of stars, it's easy to feel insignificant. But these same galaxies also remind us that we are part of something much larger than ourselves. The very atoms that make up our bodies were forged in the hearts of long-dead stars. The Earth and the solar system formed from a swirling disk of cosmic debris, and we, along with everything we have ever dreamed of, are made of stardust. We are not just on this planet, we're part of this universe. Have you ever looked up at the night sky and felt a sense of overwhelming wonder? You're not alone. Humanity has been gazing up at the stars for as long as we've existed, searching for answers, finding inspiration, and striving to understand our place in the universe. One of the most captivating features of the night sky are the galaxies, vast islands of stars scattered throughout the endless expanse of space. But have you ever wondered what the future holds for these majestic islands of light? What will become of our very own Milky Way? How will other galaxies evolve, and what does it all mean for us? Join me as we take a journey through time and space to explore the fascinating future of galaxies. Before we begin, be sure to subscribe for more updates. The Milky Way Andromeda collision. In about 4 billion years, the most dramatic event in our galaxy's future will unfold. A collision with the Andromeda galaxy. Though the word collision suggests violence, the vast emptiness of space means that stars themselves are unlikely to crash into one another. Instead, the gravitational dance will stretch both galaxies, pulling out long tidal tails of stars and gas, reshaping their structures. Over the next few billion years, the two galaxies will pass through each other multiple times before finally merging into a single giant elliptical galaxy, sometimes nicknamed Milky. The Sun, by then an aging star, will orbit in a radically changed environment, perhaps flung outward into the galactic halo or drawn closer to the new center. From Earth, if it still exists, the night sky will be filled with the blazing swirl of colliding galaxies, a sight unmatched in cosmic beauty. But the grand collision is not merely a spectacle, it's a pivotal moment in the life cycle of galaxies. Collisions are the cosmic equivalent of shaking up a sleeping giant, triggering bursts of star formation that illuminate the darkness with brilliant new stars. Entire spiral arms can be flung out into the intergalactic void, creating spectacular stellar streams that persist for millions of years. The meeting of Andromeda and the Milky Way will reshape not only our galaxy, but the orbits and properties of countless star systems within it. Some will be flung into the depths of space forever, while others will find themselves catapulted toward the center of the newly formed galaxy. For the civilizations that might one day call these systems home, the night sky would blaze with unprecedented brilliance, as countless stars ignite in the wake of the collision. Entire star clusters could be tossed into the galactic core, adding their light to the growing brilliance of the central regions. Imagine standing on Earth and witnessing the grandeur of colliding galaxies. The sky would be ablaze with light as the Milky Way and Andromeda pass in front of the backdrop of distant stars. It would be a sight to behold, a testament to the immense power and beauty of the natural world. The fate of star formation, but as galaxies merge and age, their star-forming fuel, cold hydrogen gas, is gradually consumed or expelled. Already many galaxies and dense clusters have shut down star formation, leaving behind only old red stars. Eventually, the Milky Way-Andromeda merger will also exhaust its gas, transitioning into a red and dead galaxy. Galaxies transform from bustling metropolises of star formation into quiet suburbs of aging stars. Once vibrant cores turn into colossal bulges, home to millions of old red giants and white dwarfs. The birth of new stars fades, leaving behind only the faint glow of a dying generation. With no fresh fuel for new stellar furnaces, galaxies become graveyards of cosmic dust and stellar remnants. Black holes, now dominant in the galactic cores, slowly consume the last vestiges of star stuff. It's a slow and somber end to a once vibrant chapter in the universe's history. The last stars wink out one by one, leaving only darkness and the thin glow of background radiation. Even the grand spiral arms, once cradles of stellar nurseries, succumb to the relentless march of time, fading into cosmic oblivion. Without the energy to maintain their majestic sweep, they dissolve into a chaotic jumble of old stars and dust. For those who might dwell in galaxies stripped bare by time, the night sky would be an empty canvas. A chilling reminder of the universe's relentless march toward darkness and stillness. The expansion of the universe on even larger scales. Galaxies themselves are being carried apart by the expansion of the universe, driven by a mysterious force called dark energy. Galaxies gravitationally bound into clusters will remain together, but over billions of years, distant galaxies will slip beyond our cosmic horizon, receding faster than light can bring their signals to us. In perhaps 100 billion years, observers within the Milky Way Andromeda remnant may no longer see other galaxies. The wider universe will vanish from view, leaving only a single, isolated galaxy adrift in darkness. The relentless expansion of the universe will carry galaxies away from each other, turning the rich tapestry of the cosmos into a fragmented quilt of isolated islands. As time marches on, familiar neighbors become distant strangers, lost beyond the veil of the cosmic horizon. Galaxies will drift into the darkness, their light fading into the abyss of infinite space. Only those bound tightly within local clusters will remain visible, trapped in a shrinking circle of fireflies, amidst an encroaching darkness. Within this doomed assembly, gravitational forces will continue to sculpt galaxies, but without the influence of outside forces, leading to strange and unexpected structures. Mergers and close encounters will dramatically alter shapes, creating misshapen galaxies unlike anything seen in the universe's youth. Isolated rotators will spin ever faster, flinging stars into interstellar exile. For any future civilization within these doomed clusters, the sky will be a tragic panorama of fading lights, a constant reminder of the universe's inexorable march toward solitude. The long silence, heat death of the universe in the deepest future, trillions upon trillions of years. Ahead, galaxies themselves will dim, stars will burn out one by one. Black holes will dominate, slowly evaporating through Hawking radiation. The last embers of starlight will fade, leaving only darkness and the thin glow of background radiation. In the face of the heat death of the universe, the very concept of time itself begins to lose meaning. As the last stars wink out, the universe stretches on in an endless night, devoid of new events, new life, or new hope. All that remains is the faint whisper of a dead universe, a chilling echo of a reality that once burned bright with stellar fire. The tapestry of existence, once vibrant with color, fades to shades of gray as stars die and black holes evaporate. Galaxies, once majestic islands of light, dissolve into cosmic dust. Planets, once cradles of possibility, turn cold and barren. Even time itself seems to slow to a halt, stretching into an eternity of nothingness. For any beings unfortunate enough to exist in the final moments of the cosmos, the universe would offer little more than a silent, empty darkness, broken only by the faint whisper of dying black holes. The night sky, once a canvas of infinite wonder, becomes a shroud of infinite despair. Our place in the cosmic story, and yet here we are at a privileged moment in cosmic history. We live in an age when galaxies shine brightly, when stars are plentiful, and when the universe is still young enough to reveal its secrets. We can look up and see the Milky Way stretched across the sky, and with our telescopes peer back billions of years to the first galaxies. Our species has only recently awakened to this perspective. For most of human history, we did not even know galaxies existed. Today we know that they number in the trillions, shaping the structure of the universe and the conditions of our own existence. Galaxies remind us of two truths at once: our smallness and our belonging. We are tiny residents of one star and one galaxy, but we are also participants in a universe of unimaginable scale, bound together by the same laws of physics, made of the same atoms forged in ancient stars. The galaxies are not just distant islands. They are the architecture of the cosmos itself, the stage upon which the drama of creation, evolution, and destiny unfolds. And in understanding them, we come closer to understanding our own place in the universe. As we gaze up at the magnificent tapestry of the night sky, let us remember that we are part of something much greater than ourselves. We are citizens of the cosmos, linked to every star and galaxy by the invisible threads of existence. Let us marvel at the beauty and complexity of the universe and strive to understand our place within it. For in doing so, we discover not only the secrets of the cosmos, but the secrets of our own humanity. Closing narration. Galaxies are the cities of the cosmos. Vast, luminous, and ancient. They are born, they grow, they collide, and they fade. And for a brief moment in time, one small civilization within one such galaxy has opened its eyes to witness them. In the grand story of the universe, galaxies are both the background and the protagonists. And as we study them, we uncover not only the history of the cosmos, but the story of ourselves. Thank you for joining us on this journey through the fascinating future of galaxies. If you enjoyed this video, be sure to hit the like button and share it with your friends. Don't forget to subscribe for more updates on all things space exploration. Till next time, keep looking up.